Hello everyone, in this video we introduce DreamScene, a pioneering 3D Gaussian-based text-to-3D scene generation framework via formation pattern sampling. Current text-to-3D scene methods can be mainly divided into two categories. The first is in painting-based methods, like Text-to-Room and Text-to-Nerf, which generate 3D scene representations by iteratively inpainting the current rendered images through the set camera trajectory. The second is combination-based methods, which primarily generate scenes by centering the camera around the room, or generating layouts for individual 3D objects in the scene, and then placing existing 3D representations. And what is the current problems faced by text-to-3D scene? The current methods mainly face issues such as inefficient scene generation, visual inconsistency in 3D, and limited flexibility in editing, due to their generation algorithms and fixed camera sampling strategy. To address these limitations, we propose a framework called DreamScene. First, we decompose the scene text, then generate individual high-quality objects using formation pattern sampling, place them into the scene, and finally, create the environment using a three-stage camera sampling strategy. For scene text decomposition, we employ prompt engineering within GPT, decomposing the text that describes the scene into text descriptions of individual objects in the scene, which meet the input requirements of the pre-trained text-to-image diffusion model. Our formation pattern sampling is designed based on the pattern of 3D object formation, mainly divided into three parts: multi-time-step sampling, 3D Gaussian filtering, and reconstructive generation. Our method builds upon DreamFusion. They use score distillation sampling to distill information from a random time step t. In the pre-trained 2D text-to-image model into the 3D representation at each optimization iteration. However, we found different time steps t in the pre-trained diffusion model provide different information to the 3D representation. As shown in the figure, when time step t is small, the 2D diffusion model provides more detailed and realistic surface textures, of which the shape is consistent with the current 3D representation, but lacks in providing rich semantic information of prompt. When t is large, the 2D diffusion model offers abundant semantic information, but its shape may not align with the current 3D representation, e.g., the orientation of the man, the color of the chair, the direction of the cooker between t values of 600 to 800. So in the multi-time step sampling, we integrate information by sampling multiple time steps from a pre-trained 2D text-to-image diffusion model at each iteration. Excessive Gaussians can hinder the optimization process. Therefore, we use 3D Gaussian filtering to remove redundant internal 3D Gaussians during the generation process, and calculate the score for each Gaussian using a formula. Gaussians that are closer to the rendering plane and have larger volumes receive higher scores. Based on the viewpoint in MTS, at the end of the optimization, we can directly use the information from smaller t to optimize the texture details of the object surface. Specifically, we render images under different camera poses, add noise, and then use a one-step denoising formula to obtain images with the same shape but clearer texture. We then generate 3D representations directly using a reconstruction method. In the camera sampling process, scene generation occurs in three stages. In the first stage, we generate a coarse representation of the surroundings. We freeze the 3D Gaussians parameters of the ground and objects, sampling camera coordinates within a certain range of the center to optimize the generation of the surroundings. The second stage primarily generates the coarse ground. Parameters of the environments and objects are frozen. Indoor scenes are divided into object-based regions, with camera poses sampled each iteration to focus on these regions and the room's ground. Outdoor scenes are divided by radius into concentric circles, with camera poses on different circles sampled each iteration in the same direction, optimizing ground generation. In the third stage, we use all the camera poses above to ensure a scene-wide view and refine all environmental elements. Next, we present the experimental results of DreamScene. This is a comparison of our FPS on a single object with other text-to-3D methods, showing that we can generate higher quality 3D representations in a shorter amount of time. This is a comparison of DreamScene with other scene generation methods, demonstrating that we have excellent generation quality from any viewpoint. These are the results of DreamScene's outdoor scene generation. These are the results of DreamScene's indoor scene generation. These are editing results DreamScene, showing that it can flexibly add or remove objects in the scene, change the scene style, or modify the scene structure. Thank you all for watching. For more details, please visit our project homepage and access the code.